Welcome back to next session. It is very simple session where we are going to see few problems on vapor absorption system. So these are the topics in this unit, and still we are in first topic where we are going to see the vapor absorption system and its problems. In last session we have seen the complete working of vapor absorption system. By applying those principles, we have seen the small derivation for COP, and we have done a few equations. So we have come across those equations. Now we are going to use them in our problems. So problem number 1, in a vapor absorption refrigeration system, heating, cooling and refrigeration take place at the temperature of 100 degrees Celsius, 20 degrees Celsius and minus 5 degrees Celsius respectively. So here the system heating, cooling and refrigeration. Heating is happening at 100 degrees Celsius and cooling is happening at 20 degrees Celsius and refrigeration taking place at minus 5 degrees Celsius respectively. Find the maximum COP of the system. So it is vapor absorption system. So here it is the TG is 100 degrees Celsius. So T generator, this is the temperature through generator, and through condenser it is 20 degree Celsius, and through evaporator it is minus 5 degree Celsius. So we are converting that into Kelvin. So that is centigrade Celsius plus 273 becomes Kelvin, and COP directly you can substitute in this formula TE divided by TC minus TE into TG minus TC divided by TG equal to 268 divided by 293 minus 268. So into 373 minus 293 divided by 373. So it is 2.3. COP is 2.3 for the given system. So it is very simple problem, and it is a 2-mark question. It is a 2-mark question. You can practice this type of problems for 2 marks. So problem 2, second problem. So here in an absorption type refrigerator, the heat is supplied to NH3, that is ammonia generator, by condensing steam at 2 bar and 90% quality. The temperature in the refrigerator is to be maintained at minus 5 degrees Celsius. Find the maximum COP possible. So here, if the refrigeration load is 20 tons and actual COP is 70% of maximum COP, find the mass of steam required per hour and take temperature of the atmosphere is 30 degrees Celsius. So these are the given data. So P equal to 2 bar, pressure is 2 bar, X equal to 90% of Tg. So 90% of we have quality, 90% of quality, and Tg equal to minus 5 degrees Celsius. So that is into Kelvin, and Q equal to 20 ton of refrigeration, and the actual COP is 70% of maximum COP. Tc equal to 30 degrees Celsius. So that is 303 degree Kelvin. So maximum COP from steam tables. So we have to use steam tables, students. All of you have the steam tables. Plenty of copies available in our library. You can collect from that. Otherwise, it may be hardly 50 rupees in a bookshop. You can purchase a table. You can keep with you for ready reference. So from steam tables, we have to find this. So we find that the saturation temperature of steam at 4 bar pressure is Tg equal to 120.2 degrees Celsius. So that we convert into Kelvin. So we know that maximum COP is the same formula. So by substituting all these parameters, we are getting 1.756. So this is the maximum COP, and actual COP can be calculated. So 70% of this is the actual COP. So mass of steam required per hour, we know that the actual COP is the actual heat supplied divided by HFG. So here the 3417.4 divided by 2201.6. So here this is 1.552 kg per minute. So here that if you convert into hour, it comes as 93.12 kg per hour. So that is the mass of steam required per hour. So then next problem, in an aqua ammonia absorption refrigeration system of 10 TR capacity, the vapors leaving the generator are 100 percentage pure NH3 saturated at 40 degree centigrade. So the evaporator, absorber, condenser and generator temperatures are respectively given, that is minus 20 degrees Celsius, that is evaporator, and 30 degree Celsius, that is condenser, and 40 degrees Celsius, that is for generator, and 70 degrees Celsius respectively. At absorber exit strong solution, that is the high pressure solution, the concentration of ammonia is in solution is X, that is equal to 0.38, and enthalpy is equal to 22 kilojoules per kg. At generator exit weak solution, X equal to 1 and H equal to 695 kilojoules per kg. Now we have to determine the mass flow rate of ammonia in the evaporator. So carry out overall mass conversion and mass conversion of mass conservation and mass conservation of ammonia in the absorber to determine mass flow rates of weak and strong solutions. So determine the heat rejection and absorber and condenser. So heat added in generator and COP. So this much we have to find from this problem. So here these are the given data. Q E equal to 10 TR and T6 equal to 40 degrees Celsius, T equal to minus 20 degrees Celsius, TA equal to 30 degrees Celsius, TC equal to 40 degrees Celsius, TG equal to 70 degrees Celsius. So X2 equal to X3, that is equal to 0.38, and H2 equal to H3 equal to 22 kilojoules per kg, X4 equal to X5, so that is equal to 0.1, H4 equal to H5 equal to 695 kilojoules per kg. So the aqua ammonia absorption refrigeration system, from the pH diagram we find that enthalpy of saturated ammonia. So this is pH diagram. pH diagram also it is a chart already we have used in our earlier unit. So please make use of the same pH diagram. We find the enthalpy of saturated ammonia at 40 degree. So at 40 degree you have to find this value enthalpy. So H6 equal to 1473 kilojoules per kg. So enthalpy of saturated ammonia liquid at 40 degree Celsius, so that is Hy equal to H6, so that is 373 kilojoules per kg. And at enthalpy of saturated ammonia vapor at minus 20 degrees Celsius, so H1 equal to 1420 kilojoules per kg. Mass flow rate of ammonia in the evaporator. So we know that the mass flow rate of ammonia in the evaporator is M1 equal to 210 QE divided by H1 minus H8. So that is 210 into H divided by 1420 minus 372, that is equal to 2 kg per minute. So this is the first answer. So now we will define all the Q's and T's, and from all the components in the vapor absorption system. First we will depict a picture. So this is the picture, and you can see here this is one. So low pressure NH3 that is coming from the evaporator. So that is heat absorbed is QE. So that is the input to the absorber. So this is the last step, and that becomes the first step because it is a cyclic process. And absorber cooling water is given. Q heat rejected is QA here, and strong solution from absorber and weak solution to absorber. So that is 4,5, and 4,5 is coming from here. And now the vapor is the input and strong solution is the output from absorber, and now that becomes the input to the generator, strong solution. So 2 3, and now you have this 4 5, that is the weak solution to the generator, and the NH3 vapor at high pressure to the generator. And now this is the generator process, and generator is connected to the condenser. So high pressure NH3 is input to the condenser, and 7 is the output from the condenser. So this is the cyclic process. And now once we get all the parameters, and once we get the clear picture of all these parameters, we can solve the remaining steps in this problem. So mass flow rate of weak and strong solutions, and let M4 and M2 be the mass flow rates of weak and strong solutions, and considering the overall mass balance of NH3 in the absorber. So that is a figure. So in the earlier I have shown you, so that you refer, and M1 plus M4 equal to M2, and considering the material balance of NH3 in the absorber. So M1 x1 plus m4 x4 equal to m2 x2, so that is equal to m1 plus m4 into x2. So by balancing this, m1 x1 minus x2 equal to m4 x2 minus x4, so this is equal to in terms of 0.22 m4. So for NH3 vapor x1 equal to 1, and M4 becomes 5.636 kg per minute. So this is the mass flow rate of weak and strong solutions. So that is M4, and M2 is equal to M1 plus M4. So that is equal to 2 plus 5.636. So that is equal to 7.636. So that is M2. So M2 is the strong solution mass, and M4 is the weak solution mass. So these are the two we have to find. Actually. So this is the answer for the second step. So third step. So heat rejection in absorber and condenser. Considering energy balance of the for the absorber, the heat rejected to the atmosphere or cooling water, QA equal to M1H1 plus M4H4 minus M2H2. So by substituting all these values, so QA equal to 6589 kilojoules per minute, and heat rejected from the condenser, so that is the C diagram you can refer, and QC equal to M6H6 minus H2, so that comes 2202 kilojoules per minute. Heat added in the generator, considering energy balance for the generator, heat added in the generator, so that is the B figure in the diagram. So Qg equal to this equation, so M4H4 plus M6H6 minus M3H3. So by substituting all these values, we are getting 6695 kilojoules per minute. So that is the answer for heat added in the generator. So COP by substituting Q E by Qg, so that is equal to 10 into 210 divided by 6695 kilojoules per minute equal to 0.3137. So this is the COP of this system. Obviously, it is very low in terms of its performance. So coming to next problem number 4. A simple absorption refrigeration cycle does not consider the refrigeration column and preheating exchanger. In such an aqua ammonium cycle, the evaporator, absorber, condenser and generator temperatures are given. So 233 Kelvin, 303 Kelvin and 313 Kelvin and 373 Kelvin respectively. The properties of aqua ammonia are as follows. So this is the table given. So enthalpies are also given. So strong solution leaving the absorber, so that is the concentration kg of NH3 per kg, so that is 0.421, and enthalpy is 30, and weak solution leaving generator is 0.375, so enthalpy is 340, Water vapor generator equal to 0.945. So enthalpy is 1870. So liquid leaving condenser is 0.945 and 470 enthalpy, and vapors leaving evaporator is same 0.945 and 1388 is the enthalpy kilojoules per kg. So this is the problem statement. Draw schematic diagram of the system. So schematic diagram already we have drawn earlier in earlier session. So same diagram you can draw and show here. So for 1 ton of refrigeration capacity, determine the mass flow rate of the solution in the evaporator. Consider overall mass balance and material balance or partial mass balance of NH3 in the absorber. So this will give two equations, solve them to determine mass flow rates of strong and weak solutions. So consider energy balance for the absorber and generator to find absorber heat rejection and generator heat transfer. So find condenser heat rejection ratio. So we have to find the condenser heat rejection ratio. Check the overall energy balance neglecting pump work and then find COP. So pump work is neglected here and we have to find the final COP. So this is the problem statement. So for this all the data are given in the problem itself, so we can directly solve this problem. So given data, so TE equal to 233 Kelvin and TA equal to 303 Kelvin, TC equal to 313 Kelvin, TG equal to 373 Kelvin. So already I have already converted into Kelvin, and X2 equal to 0.421 and H2 equal to 30 kilojoules per kg and X5 equal to X6, so that is equal to 0.375. So H4 equal to H5, that is equal to 340 kilojoules per kg, and X3 equal to 0.945. So it is from the table. So H3 equal to H6, that is 1870 kilojoules per kg, and X4 and X7 is equal to 0.945. So H7 and H8 470 kilojoules per kg. So X8 is also 0.945. So H9 is 1388 kilojoules per kg. QE equal to QG, that is equal to 1 ton of refrigeration. So that is equal to 210 kilojoules per minute. Already we have seen this value in last unit. Please remember this value always. So schematic diagram, you can draw simple variable, that is the vapor absorption refrigeration system we have seen in last session. Same diagram you can draw this. So that is the first step is over, and second step, mass flow rate of solution in the evaporator. We know that the mass flow rate in the evaporator is, so M1 equal to 210 QE divided by H1 minus H8, that is equal to 210 into 1 divided by 1388 minus 470. So this comes around 0.2288 kg per minute. So third step, mass flow rates of strong and weak solutions. So M4 and M2 be the mass flow rates of strong and weak solutions respectively. So considering the overall mass balance NH3 in the absorber, so M1 plus M4 equal to M2. So, and considering the material balance NH3 in the absorber, so M1X1 plus M4X4 equal to M2X2. So that is equal to M1 plus M4 into X2. From equation 1, 0.2288 into 0.945 plus M4 into 0.375. So that is equal to, in terms of M4, we are getting this equation by solving this, M4 equal to 2.606 kg per minute. So, and M2 can be find out now because we know M1 as well as M4. So by adding these two, we are getting M2 equal to 2.8348 kg per minute. So this is the mass flow rates of strong and weak solutions. So here M4 is the strong solution and M2 is the weak solution. So mass of weak solution. So M2 is the mass of weak solution is 2.8348 kg per minute. So this is the step 3 solution, and we have to go to step 4. Absorber heat rejection, generator heat transfer, and condenser heat rejection. So considering energy balance for the absorber, the heat rejected to the atmosphere or cooling water, so that is QA equal to M1H1 plus M4H4 minus M2H2. So by substituting these values, so QA is 1118.57 kilojoules per minute. So this is the one answer. And considering energy balance for the generator, heat given to the refrigerant in the generator is Qg. So same mass equation is used here, M4H4 plus M6H6 minus M3H3. So by substituting all the values, so here the generator heat balance, that is the considering the heat 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 through generator is find out as 1228.852 kilojoules per minute. So that is the Qg. So Qa absorber heat already we have find out, and now Qg, that is the generator heat transfer. Now we have to find the condenser heat rejection. So the heat rejection from the condenser is equal to Qc M6H6 minus H2. So by substituting these values, we are getting 320.32 kilojoules per minute. So this is the answer. This is the fourth step. Fourth step is completed. So QA, QG, and QC, all three we have found out here. So next is the check. This is the last step. We have to find the overall energy balance and COP. So heat absorbed by the generator and evaporator. So considering the overall energy balance, the heat absorbed by the generator and evaporator must be equal to the heat rejected from the absorber and condenser. So heat absorbed by the generator and evaporator, so Qg plus Qe equal to 1228.852 plus 210. So that is equal to 1438.852. So heat rejected from the absorber and condenser. So Qa plus Qc equal to 1118.57 plus 320.32. So that is 1000, same similar, very similar value. So that is 1438.18 kilojoules per minute. Since the heat absorbed and heat rejected are very close, the overall balance is checked. So here both are almost the same. So both are checked here. The overall balance is achieved here. Now we have to find the COP. So COP equal to QE by QG. So by substituting the values, that is equal to 0.171. So this is the COP of this particular system. So now we have found all the 5 steps, and now you have to find step by step like this. So all the formulas you have to remember carefully, and you have to substitute the values. Almost all the values will be given in the problem statement. If not given in the problem statement, you have to take the pH chart, and from that chart you have to take the values, and steam tables also keep with you ready. And in exam, please carry these two, steam tables and pH chart. So there ends simple problems on this. We will move on to next topic in next session, that is Electrolux refrigerator, that we'll see in next session, students. We stop here, and these are the references. You can refer, as I said earlier, you can refer Kurmi book, and also you can refer Aurora and Rajput. We stop here. Thank you, students.